about a Reidemeister-Singer conjecture of surface diagrams.
So I'm saying it's a conjecture mainly because of the number of people who actually believe it's a theorem is probably less than that threshold amount at which something becomes a theorem. The paper should appear for too long.
One counterexample.
I'm sorry?
Usually one only needs one counterexample.
Okay, so there's this familiar theorem about symplectic four-manifolds, at least, that solutions to the Seiberg-Witten equations correspond to pseudo-holomorphic curves on your given four-manifold. There's a slight sort of start for a generalization that appeared in 1999. Basically, suppose your symplectic form omega, suppose it actually vanishes on a collection of circles and B2 plus is greater than 0. I think actually you might go ahead and say greater than 1. I guess I'll go ahead and say that, even if it might be weaker. And also, not all of the Seiberg-Witten invariants vanish, and not all then, so you choose an almost complex structure that is compatible with this omega, of course away from its vanishing locus. Then there is a, I guess I'll say J holomorphic because I don't want to write pseudo-holomorphic. Right, so that would be the starting point of what I'm wanting to work, what I've been working on. This, I'm not exactly sure if this is what people would call Taubes' program, but essentially the question is, can you make this stronger in the sense that for a near symplectic four-manifold with B2 plus greater than 1?
So you have some requirements how the omega looks like in this theory or not, near the circles.
Is it self-adjoint? Do you think it's self-adjoint?
Well, okay, so at least for the situation that I'll be considering, omega is a symplectic form away from a collection of disjoint circles on which it vanishes in a transverse way. So I don't think he has those assumptions in his paper.
Well, he started with some assumptions at some point, and later. So Lattinger had a theory about under certain conditions that you have this omegas existing, and then they have certain properties how they vanish on circles, and later Taubes could prove that theory. And then he had in a certain time period he didn't require too much how omega I think vanishes. And then later, and what kind of complex structure he chooses. And then he ran into some difficulties, and then he later adapted what I had done with the Vysotsky and Sehner, where you have sort of viewed as, when you can take these omegas that have a very particular behavior, so that you have a context structure near the circles, some overtwisted context structure, and then you take J's adapted to this. And that's presumably where I think what you're referring to, Taubes' program would take place. For this kind of more specific things.
I see. Well, the very most general sort of motivation that I'm trying to impart is simply that we would like to see the Seiberg-Witten invariant as a type of Gromov invariant where you allow the symplectic structure actually to vanish on circles. And this actually greatly increases the number of manifolds that you can have, right? I mean, all you need is that the intersection form is indefinite. Then you can construct such a thing. But anyway, this is where it starts. And one way that people have been trying to do this is by equipping your manifold with something that resembles a surface bundle over a surface. And then you look at compatible so these forms that vanish on circles, they're called near symplectic forms. And what you do is you equip this fibration-like structure with a compatible near symplectic form. All that means is the two form restricts to a volume form on each fiber, away from its vanishing locus, of course. I'm sorry, I'm not writing very much down. This is the hardest part of the talk, actually, is the motivation. So I guess I should start with that. To see SW as a Gromov type invariant for near symplectic manifolds. It is simply that you count J holomorphic multisections of some surface bundle like structure on your four-manifold. So what is a multisection? Essentially, locally, it is a section, but it could wrap around multiple times and have multiple intersections with a generic fiber. So that's the motivation. Basically, people have defined these things, and sometimes it works. For instance, there's this thing called a standard surface count that was defined by Donaldson and Smith, which in the case that M is actually symplectic, you can, after possibly blowing it up, give it a Lefschetz vibration and count multisections in that case. And it coincides by work of Usher with the Seiberg-Witten invariant of that four-manifold. So to reiterate, the approach works for symplectic. Four-manifolds. Okay, so what about near symplectic? Well, the approach that we're using, the approach that I'm going to be talking about are broken Lefschetz vibrations. So maybe I should say that. So a broken Lefschetz vibration is simply a Lefschetz vibration where you allow one additional type of critical point. Right, so what is that type of critical point? And I'm just going to draw a picture, though there are equations for it. So to sort of introduce the notation, there's this Lefschetz critical point. And the way I'm going to draw that, well, I'm going to draw a picture of the base of the map. So in this case, a Lefschetz critical point is an isolated point. It maps to a point in some two-manifold. And the way that I'm going to depict it is just by drawing its vanishing cycle. So away from this point, the generic fiber is a surface. As you approach this point, a simple closed curve on your fiber shrinks to a point, and you get a nodal singularity above this point. So I'll just draw a little circle somewhere. And then I draw an arrow to say, as you approach that point, that circle shrinks. So this is something called a base diagram. It's a diagram of the base of your fibration. So there are more critical points. There is a fold. And the way this looks is, in your base diagram, it's a surface bundle over a surface, except you've got this arc of critical points. And at every point in this arc, you see the following sort of thing happen. Here's another surface, and you have a vanishing cycle again. And as you approach any point, that vanishing cycle shrinks, and you get a nodal fiber above every point in this arc. As you move past it, it does something like this, where what has happened is the two little cone points that you have above here separate, and you lose genus. Or sometimes, if this thing separates the surface separates into two pieces. So basically, all I'm describing, really, if you restrict to a horizontal line here, is an index 1 or 2 Morse critical point, depending on which direction you're moving. And actually, maybe I should be a little more careful about this. We don't need to draw the whole fiber, do we? We could just draw a neighborhood of that critical point, just to be extra clear about what it actually is doing. You've got some cylinder, and going around that cylinder, that arc shrinks and you get two disks. And these pieces could all be considered pieces of some larger fiber. So actually, what I've drawn here is a picture of a 4-ball to the 2-ball. Because as you start from, say, this side, you see R3 starting to get swept up by hyperboloids. Then you get that double cone, and the rest of R3 is swept out by the two disks that sort of fill in the little parts above and below. So this is a map from a 4-ball to the 2-ball. The final one that I want to talk about is the cusp. And what this looks like, downstairs you've got two fold arcs, and they meet at a cusp point. So the actual cusp is a point in the fiber above that, right there. It's an isolated point in your four-manifold. And what happens there, you've got two different vanishing cycles now. And the requirement is that one of these vanishing cycles, well, you can pick that one. The requirement is that the other one intersects it transversely at a single point. I'm surprised IAS doesn't pay for hair and makeup. I'll put it on upside down. I'm just going to rub. Okay.
The point is, it's a linked pair of vanishings, of loops, yeah? Or is that important or not?
I suppose you could consider them linked, but the requirement...
It's intersected, sorry, I mean the intersecting.
Yes, the requirement is that these two have to intersect at a unique point. I've drawn another, so on the other side, the fiber is a disk.
So if you're below this was contracted. If you're above, the other was contracted, and if you're in the singularity, both are contracted.
Right, right. So the way I imagine the fiber above this is going to look something like that. It's not, right, it's a singular fiber above that cusp point there. But if you think about it, sort of in the privacy of your own office, as you look at, so certainly a vertical line here is just a map from the 4-ball, or a map from the 3-ball to a line segment. As you move toward the left, this is a model of the introduction of a pair of canceling Morse critical points. And this is precisely the sort of thing that you would see when you're looking at the stabilization of a Heegaard diagram, for instance. You get this one parameter family of maps to the interval. Those intervals, you look at the critical values, it sweeps out something that looks just like this. Okay, so the fact is, this was not my work, this is work of Berkeley. You can perturb this critical point in a generic direction, and you end up with something that looks like this. You get a circle with 3 cusps. Just an arbitrarily small perturbation of this puts you into maps of this type. And so we're actually not going to talk about Lefschetz critical points at all, but through pretty much the entire talk, you might consider this a talk about broken Lefschetz fibrations, where broken Lefschetz fibration means this type of critical point and this type. But really, I'm going to be talking about these two. Yes. So there is another kind of fold called a definite fold. And what that one looks like is a sphere shrinks to a point, and then you've got nothing. And four-dimensionally, what this looks like is as if you had like a four-dimensional piece of paper or something, and you actually folded it and then projected it down. If this was 2 dimensions, you would have 2 points, a zero sphere, that as you approach the actual place where you folded it, they shrink down and then disappear. So that's where the word comes from. There are lots of different types of folds. In fact, well, for 4 manifolds, there's only this one and that one. But when you go up higher, the thing is, as a Morse function, as you go across here, there are different indices, and so you can have different types of these folds. Mm-hmm. A Heegaard diagram? Well, to stabilize a Heegaard diagram, I'll get to that later, but it comes down, it's this Reidemeister-Singer theorem that I was talking about. But okay. In fact, you don't have to know any 3-manifold anything for this, but it gives you perspective. Okay. So there are certain moves that you can do with these types of maps. One is called birth. And what that entails is you start off with a blank diagram. This is a map from the 4-ball to the 2-ball, where you simply project out a 2-dimensional direction, right? So D2 cross D2 maps to D2. It's a blank diagram. What you can do, or you can do the reverse, is you can open up a circle of critical points like this. Now, judging by this local model here, what happens is, on the inside, the fiber is a torus. And you've got 2 vanishing cycles, like that. And that's just, this is done by a homotopy of your map. Another one is called merge. And what that looks like, sort of, I don't want to go into all the details of when you can actually do this, but when you have 2 arcs like this, and you've got, what you can do at some point is you can bring them together. Have I done this? Yeah, I did it backwards. You can go like that. So I'm leaving a lot of details out, but essentially these 2 things shrink together and you get this. Now, judging by, if you use a point here and here through the entire homotopy, you see that there is sort of a requirement for what's going on, right? Namely, there are vanishing cycles as you approach this one, and they have to intersect transversely at a single point. So this is called a merging move. And this is not actually part of the moves that I'm going to be using, but combinations of these moves do what I want. So there's birth and merge. Another move is a flip, where you can start off with an arc, and then you can do something along these lines. You've opened up sort of, this thing kind of crinkles up for a second and then passes, and you get something that looks like this. You can introduce a flipping move. Finally, isotopy. And this is the most mysterious of the moves. There are things like, if you have a piece like this, you might grab a little bit of it. Oops, that's not good. Maybe I'll just say something like this. If you have two arcs, sometimes you can do something like this by a homotopy of your map. That happens under special circumstances. Basically, it is a homotopy that does not change the critical submanifold of your four-manifold, but it looks different downstairs. So, in my thesis, I was able to show that these moves, so a theorem is that if two, I'm going to call these broken Lefschetz fibrations because they're interchangeable with them. If two broken Lefschetz fibrations are homotopic, try the other side. I keep hitting it with the chalkboard. There, all right.
Okay, yeah. There you go.
Okay, so basically the theorem is that if two such maps are homotopic, you can get between them by some sequence of these moves. So it's a uniqueness theorem for these maps. But the problem, so problem. Maybe. Okay, so here's a sphere, and here's a bunch of fold arcs and cusps, and it's just a mess. And what the heck do we do with that? You see, this thing that I was talking about earlier, where people were trying to look at multisections, well, you can define your count of multisections in this situation. But the problem is, there are all these different kinds of moves where this gets very complicated, and people have tried, and they cannot prove that it's actually an invariant when you do all these moves. It's just, there's too much that can go on. So in the same paper, I was able to show that you can use these moves to get something along these lines, where you have a single circle and it has cusps and it's embedded by the fibration map. So this I'm going to call a simplified, purely wrinkled fibration, and then instantly discard the term because all I care about is the higher genus fiber. maybe I'll go over here. In such a map, you only need the higher genus fiber. Decorated with the vanishing cycles to specify M up to diffeomorphism as long as the fiber genus is at least 3. Now the reason that I care about it being at least 3 is if this was genus 2 up here, and I gave you all these vanishing cycles, then I could construct the map down to there. But then there's more than one way to glue in the South Pole. But if you increase the genus sufficiently, then pi1 of the diffeomorphism group of this lower genus surface is simply connected, which means there's only one way to close this off. Okay, so
so you mean if the genus is 2, you know also what's the extra information you need to classify? Or
right. Well, okay. So the fundamental group of if the genus was 2 here, then that means we have a torus down here.
yeah.
And the mapping class group has fundamental group z cross z times z. So there's lots of different ways of gluing down here. If this was a sphere down here,
But
then
if
there's
you have
only
this
2
information-
ways.
If you have this information, then you
Sure, sure.
We just said, yeah, you just have to add an additional piece of information to it.
That's true, yeah. But it turns out that even that is unnecessary because there's a way of inflating the genus arbitrarily for these maps. So such a surface is called a surface diagram. For M.
So what you need is a family of curves
So I'll draw sort of
which
a,
are pairwise intersecting at one point. Every 2 of them intersect at exactly one point.
very close. Let me just draw a quick sort of example of such a map. I have no idea what the total space is, but
I know you have a sequence of them.
it is, yeah,
You
it's
have
a,
sequence of curves and each one intersects at one point with the next one. So
yes,
close curve.
exactly. So example, you could have something like this, a genus 3 surface, and you could have curves that intersect along these lines. I'm not drawing the back side. I just want you to know, for example, this curve here, it just goes around the back and comes right back, and so forth. And so this has 6 vanishing cycles. And so it would look like this, where you have 6 cusp points. And this picture here would be the preimage of this point, where you draw reference arcs down to each one and see what the vanishing cycles are.
Does it have to be periodic? Does it have to come back?
Yes, simply because this is a circle down here.
Oh,
Yeah, these curves are cyclically indexed. Yes. Okay, so what would be really nice is to discard this and just say, there are moves on these things, and then try to see these, I don't know if I've mentioned the name, but counting multi-sections of this type of map is called a Lagrangian matching invariant. Tim Peretz came up with it. Basically, each little piece of regular values here you could view as a surface bundle, and you get Lagrangian boundary conditions from each of these arcs for counting holomorphic curves with boundary. So a couple of things I need to say is surface diagrams exist for each four-manifold in each homotopy classes of maps, and each homotopy class of maps. So what I'm saying here is you give me any map from the four-manifold to the two-sphere, and I can turn it into one of these using the above moves. So why not just look at those types of maps? Notice this is a little bit more than we asked for, right? Because not every four-manifold has a near-symplectic form. But at any rate, we could at least restrict our attention to those.
But how is it if you remove one point and use a four-manifold as something just asymptotically R4 and just require standard behavior of the symplectic form? I think Latinger had a result of that kind. But it's not so clear if it were correct, however. Yeah, so he had an idea that was pre-Taubes. So he takes a four-manifold, he removes one point, so you make it open, it's like an R4 at infinity.
Okay.
And then he was looking for near symplectic forms on it which had a particular behavior at infinity. And that seemed to exist quite often. So you saw if
By removing points?
removing a point.
Well, I suppose.
You prescribed some kind of singularity at the infinity, what that form had to do. So then he was looking at, he looked at self-dual forms, but he perturbed it by some kind of a Dirac type thing.
Well,
I thought self-dual forms had generically these kind of singularities. Is that correct?
yes. Well, the types that I haven't actually described to you, but yes.
But the thing is, you need something on the second cohomology to find this guy. So they exist. But then, sort of, I think he introduced artificially certain things at that point, what they should do, and then they existed more often, or maybe always. Something like this.
So, sort of related to what, I might even just go ahead and skip the topological part and tell you what I was interested in doing with the topology I've done, which is very symplectic. So very related to what you were talking about. The idea is going to be, so let's just look at it from the North Pole. You've got something that looks like this. There's that sphere going down behind it. What we would remove is everything outside of here. So I'm taking out a little bit of the cusp at each part. And you end up with something that looks like this. All right.
I'm not sure I know where we are.
Okay. So actually, maybe I should have been a little bit more clear with what I'm drawing. The dotted line coincides with this arc here, and then dives across the cusp.
And this has 5, and this has 6 lines.
Some mathematicians count, some don't.
Yeah, there are 3 types of mathematics. Those who can count and those who cannot.
Oh, okay, you said those who can count. I said those who do count. All right. Okay, so what we're looking at here is sort of a diagram where you've got, let's say the genus is at least 3. So this looks a lot like a quilt to me, in the sense that you have these boundary conditions here obtained by picking a point inside and looking at what you get. So you get these distinguished curves here. And then you could sort of regularize at these ends in the way that you're talking about. And then try to count multisections in this particular context. I've not started on this really. I've only thought about it in the case where they're actual honest sections. But one thing that's kind of interesting is, if you look at the image of such a section, say out here or anywhere, and you've chosen a connection on this bundle-like object, then you can flow that point back and look at where it hits the fiber. And you're going to get something that starts to look a whole lot like the Heegaard-Floer picture, where you're looking at these immersed surfaces with boundary given by sums of these circles. So that's where I plan to go next. And I've done almost no work in that direction yet, so that's probably all I can say about it. The thing that really is needed, though, is a uniqueness theorem for these things. We need moves on these. And that's what I would like to claim that I've proved. And I'd like to share what those moves are, because they look a lot, actually, like Heegaard diagram moves. And I think this chalkboard's seen enough action for now. Actually, I was kind of pushed into this. When I first graduated, I wanted to try to sort of firm up the theory of quilts to deal with more complicated vibration structures. That sounds really hard. And I think that this is actually going to be a better sort of approach, sort of make the topology as nice as possible, then do the Floer theory. Okay, so moves on surface diagrams. How much time do I have?
2, 5.
Okay, that should be enough. Okay, so one of them is stabilization. So what this looks like is, suppose you've got a vanishing cycle here. What you can do is you can remove sort of a little, well, maybe I shouldn't erase it, but you can look at just a little neighborhood of a point on that vanishing cycle. And you can glue in, you can increase the genus in this way. Maybe this doesn't look quite right. I'll do it like that. So this curve, maybe I should have drawn it in a color. Maybe it's blue. This curve sort of survives looking like that. And you know that this is just one of a sequence of curves. And so you've got some other ones, say that one comes before it and then this one comes after it, for example. So these are its neighbors, okay? The blue curve's neighbors are these. So you're going to insert more vanishing cycles into the sequence in the following way. So you start with that one. Then you've got the blue one. Then you've got one over here. And then this one. And then this one again. And then you return to the blue one. And resume your sequence. Say like with this one. So I've introduced 4 vanishing cycles there. There are 4 new ones. And it has increased the genus by 1. So for Heegaard diagrams, the picture is precisely the same, except you don't have to pick a point on one of the curves, and you only introduce these 2. Right? For a Heegaard diagram, this little piece would be off on some blank spot there. But anyway, that's what the stabilization looks like. And the homotopy what it looks like is it's going to be something like, you start off with a circle. I'm not going to draw the cusps. We've zoomed out really far, I guess. And then you do 2 of those moves, which I should say these moves, those 4 that I've already erased, those were not my work either. That was also a work of Berkeley. But these moves are my work. I've used these so much. So you do these 2 things, which are called flips, and then you cancel these 2 intersection points by moving this downward. And so you end up with a square. So, okay, I told you 4 vanishing cycles, right? But this only added 3. So what's going on here? Well, if we had a little cusp in here at the beginning, now it's introduced 4, hasn't it? So the thing is, if you don't have any cusps to begin with, you don't come back to the blue one, it is the same one that you started with. So it's either 3 or 4. Basically, you increase the genus and add some curves in a predictable way. This is a stabilization move. And since at least I'm claiming that this is a homotopy of a map from a 4-manifold to the 2-manifold, this diagram represents the same 4-manifold because it comes from a homotopic map. And I'm also kind of sweeping a little bit under the rug here, just as there is some freedom when you stabilize a Heegaard diagram. I guess I should have said this, but that middle curve that intersects the blue one, I think I'm just going to stick with that. Basically, this is just slightly more complicated than it looks. There are other possibilities, but they all look pretty much just like this. Okay, there's that stabilization move. There's a handle slide move. So what this looks like is, if you had something along these lines, you had a circle, and then here are its neighbors, okay? So these 3 are consecutive curves, and then here's this one. Who knows where it is, but it's not one of these 3, right? So maybe I could sort of draw a base diagram to show what I'm talking about. So let's say this is the blue. And so the blue one corresponds to that arc right there. And then its 2 neighbors are going to be these 2. And then let's say that this one, maybe I'll make that red. Let's say that that one is this one over here. Notice, I had to make it this one, because otherwise the red one would have to intersect one of the white ones, right? Because it would be adjacent. So it has to be sort of separated also in the fold locus. But what you can do in this situation, so to be explicit, let's say that this is A, B, C, and D. A, B, C are consecutive. And disjoint from D. So what you can do is you just sort of imagine that there is a disk whose boundary is D. And you're going to take this blue one and you snake it around over here and then slide it over that disk. This is precisely what happens for Heegaard diagrams. And what it would look like, for example, is something like this. So here's your red one. Nothing happened to the white ones. They're still sitting there like this. But now what the blue one has done is it looks like that. So that's called a handle slide. Now what this looks like in this picture is that you take this blue one No. Let me make sure I'm doing this right. It's kind of tricky to draw. Should draw the other way. Okay, so what have I done? taking this blue arc, and here's this red one. And if you remember what cusps look like, the higher genus region is in here, and the lower genus region is in here. So I've pushed this blue arc into a part of the fibration in which the vanishing cycle for this has already crushed and separated, right? So what that means is you've got a lower genus fiber out here. It looks like this. It would be something like it would look something along those lines, in which what's happened is this red one has crushed and separated, and you've got these 2 points where if you move backward over the red one, these two things come together in a self-connect sum. So when you're in this situation, you can move this blue one and just link it with one of those points. And then pull this one back, and it looks like this again. However, the vanishing cycles now look different. So that's what a handle slide comes from and what it looks like. It actually is a one-parameter family of three-dimensional handle slides. Okay. So were there anything before I moved on to basically the last part? Okay, so one thing that I want to say, though, is when you look at these deformations, you see this, and then it moves over, and then it comes back. Here's one where you've got a circle, and you just kind of open up a couple of little, candy wrapper things, and then move, and then open it back up. The thing is, both of these things preserve the homotopy class of this actual circle in your four-manifold. Right? I mean, if you simply looked at the fold locus, it would just be something wandering around in your four-manifold, and it wouldn't change its homotopy class. So the fact is, though, you've got that merging move where you can take 2 arcs, merge them together, and then unmerge them. So you can actually change the homotopy class of the critical circle. So we need a move that can achieve that. And the last move is called a multi-slide. So what this looks like is, here's a little piece of our base diagram. These are 2 fold arcs. And what you can do is you can merge them to get something along those lines. So what that means is I've chosen a distinguished arc in the four-manifold between the 2 fold arcs. And the homotopy follows that arc to do your merge. Then I'm going to choose another arc in your four-manifold. And then reverse that merge so that you get back to something along these lines. So maybe I should say this is called a merge and an inverse merge. And you get something along those lines. So what this would look like is, at least in this picture, it would be like these 2 sides came together so that you have you have a pair of squares now, and then they come back together to have another hexagon. Now the way you choose these arcs in your four-manifold can give you some control over the homotopy class of the critical loop. So I wonder how much I want to say about this. Okay, so what I've said was there are these 2 vanishing cycles, right? You pick a point in the middle and you look at this one and you look at this one. Because of the model for cusps, those vanishing cycles intersect at a unique point. So you've got some part of your fiber that has one of those in it, right? And then maybe down here I'll draw the rest of the fiber. Who knows what's going on down there? But if you pick this point here, you'll get these two vanishing cycles that after possibly a diffeomorphism of the fiber looks like this. Now the weird thing about this, and I don't want to go into why it actually looks like this, but when you break this up like this, you get a circle here and a circle here. And it's hard to relate the it's hard to relate the vanishing cycles in this upper circle and this lower circle. Maybe I should draw. When I say two squares, I mean it looks like that when you've pinched these red and blue together. It's hard to relate the vanishing cycles for this one and this one. So what we do is we pick a point in this one for the entire time, and then we're going to see what happens to the vanishing cycles here after we do the merge. And it turns out to be very strange. When you do this merging move, you get 4 vanishing cycles kind of broken off from the main family, right? And what happens is you remove this, and you've got these other vanishing cycles kind of wandering around in here. And then according to these arcs, you're going to get some kind of circle in the rest of the fiber. Who knows what it does? But it has to come back to where it was at first. And this specifies an isotopy of the surface here that only drags these vanishing cycles around with it. Once you've done that isotopy, and you have this, and you come back to this part where I slit this guy's neck, you have these little places where the vanishing cycles used to go in and out of here. And you just patch them in again. And you've changed a subset of these vanishing cycles. So this is a rather kind of mysterious and complicated move. But nevertheless, it's there. And the deformation corresponding to it looks simple, but its effect is complicated. It was a terrible explanation, but at least hopefully it gave a flavor. So the theorem that I should have said probably toward the beginning of the talk, or well, I should say conjecture then, since that's what it says for the title, is that if M is simply connected, and two surface diagrams come from homotopic maps M to S2, they are related. Of course, up to diffeomorphism. By stabilizations and handle slides. If pi 1 of m is not trivial, if m is not simply connected, adding multi-slides gets the job done. So one kind of nice aspect of this is all of these deformations that I've described are deformations at which every fiber is connected at all times. And that's something that people had been wanting for the Lagrangian matching invariant, is because it's, I mean, there are lots of ways to screw up the Lagrangian matching invariant. For instance, if you did something like this, if you just kind of took a little piece of this and moved it back, what you've done to the fiber in here is you've got, let's say that the vanishing cycle looks like that. Well, I've moved it. It needs to be the opposite way. Sorry. In order to get to this point, you have to go through the vanishing cycle once and then again. And so you've pinched off a sphere, right? One way sort of to think about it, you've got these two parallel vanishing cycles. You hit it once, then you hit it again. And so the fiber inside here is going to be two disks with a sphere in between. This sphere is necessarily null homologous. And for the Lagrangian matching invariant inside this little piece, it's like it's not even defined. So there are silly ways to get disconnected fibers that screw up the Lagrangian matching invariant. But if you restrict your attention to maps like this, that doesn't happen. So, but I don't even plan to approach it in that way anyway, but maybe others will. I think that's all I want to say.